This video is looking at intermolecular bonds. So it's intermolecular, so molecules are covalent compounds or elements. So we'll look at understanding the intramolecular and intermolecular, what the words mean, and the two particular intermolecular bonds, dipole-dipole bonds. So we're going to spend a lot of time looking at this and building it up to hydrogen bonds. Eventually we'll use this phrase most often. And dispersion forces, so the two sorts of intermolecular bonds. And so to build up an understanding of dipole-dipole, we're going to look at what a polar bond is and then what polar molecules are. So after we've looked at the intermolecular bonds, we'll look at the properties. How does this affect the melting and boiling points of polar molecules? Okay, so to remember the difference between intra and inter, you need to relate that to words that you know before. So just pause the video and write down as many words as you can think of that start with inter and intra. Okay, so inter means between. So international, between countries. Internet, between computers in different locations. Intersection, between two roads or something like that, two different things. So it's all intercellular, if you're doing biology, is the area between cells, not within cells. So within is intra. Intracellular means inside the cell. So within rather than between. The intranet, like computers all in one location, like a school. We have an intranet at our school. So within, not between. So intramolecular bonds are the bonds within a molecule. So the bonds within a molecule are covalent bonds. Alright, so we're looking at using the word looking at intermolecular bonds to explain why one molecule stays near another molecule. So to explain why all molecules aren't gases, what's holding one molecule to another molecule. Alright, so there are two sorts of intermolecular bonds, dipole-dipole, and we'll spend quite a bit of time explaining how this works, and then dispersion forces. So dipole-dipole is the overarching type of intermolecular bond, but we're going to use this specific example of hydrogen bonds most often. Alright, so to explain dipole-dipole, we need to kind of build up an understanding of what a polar bond is, and then what a polar molecule is. So we'll look at polar bonds first. So polar bonds are the bonds between one non-metal atom and another non-metal atom. And if one of the atoms is more electronegative than the other, it will we'll look at the effect on the bonding. So in the Year 11 data book, there's all of these electronegativity values. So come back to this section if you need to check some of the numbers. So these numbers under here aren't molar masses or atomic masses, they're electronegativity numbers. So fluorine has the highest electronegativity value of 4. Okay, so electronegativity, you might remember, is the ability for an atom to, how well it attracts electrons. So if we've got two atoms that are bonded, if the difference between them is greater than 1.7, so they're quite different in their electronegativity, then the bond that they would form would be ionic. So chlorine has an electronegativity value of 3. It's really good at attracting electrons, whereas sodium is 0.9. It's not very good at attracting electrons. My little mouse, where is it? There it is. So the difference between 3 and 9 is 2.1. So it's very electronegative. So it's greater than 1.7, which means that the electrons, instead of being shared, the electron from the sodium is lost to the chlorine, which is why it becomes ionic. So we're looking at molecules, so they have electronegativity difference less than 1.7, so they're closer in their ability to attract electrons. Their non-metals are both electronegative. So if they're between 0.5 and 1.7, the difference between them, then they're sharing electrons and it's not balanced. So one of the atoms is more electronegative than the other, so we would say it's polar. If the difference between them is only 0.5, so their electronegativity values are quite similar, then they're sharing electrons, covalent, and they're non-polar. They're sharing fairly equally. Alright, so let's have a look at carbon and hydrogen. Are they sharing their electrons equally, or is one more electronegative than the other? So if you look back at the table, you'd see that carbon is 2.5, hydrogen is 2.1, so the difference between those is 0.4. So basically they're very similar. Their ability to attract electrons is very similar, so they share them fairly equally between them. So it's a non-polar bond. If we looked at hydrogen and chlorine, chlorine is quite electronegative, hydrogen's not. The difference between them is 0.9, so that's greater than 0.5. So this is, they're sharing electrons, but because the chlorine has a better electronegativity, it's better at attracting electrons than the hydrogen, the electrons will spend more of their time up near the chlorine. Electrons are negative, so it makes the chlorine a little bit negative. So we use this symbol, delta, it looks a little bit like an S, to refer to slightly negative. So it's a little bit negative, not properly negative like the chlorine in the previous example, which becomes a negative ion. It's just slightly negative, and the hydrogen is just slightly positive. Okay, so we call that bond now a polar, like the north and south pole, a polar bond, because the electrons are more up one end than the other most of the time. Alright, so if you looked at the difference between these, oxygen and hydrogen, 3.5 to 2.1, so it's between 0.5 and 1.7, so it's a polar bond as well. So it's more electronegative, the oxygen. The electrons spend more of their time near the oxygen. It's slightly negative, this is slightly positive. The same for the nitrogen, 0.9. So it's also a polar bond. They spend more time near the nitrogen and spend more time near the fluorine. So these are all polar bonds. Alright, so there's the individual bonds that we've looked at so far between two atoms. Now if we build up a whole molecule, to work out if a whole molecule is a polar molecule, it has to have its polar bonds make one end or one side of the molecule slightly negative and the other side slightly positive. So it's not symmetrical, the molecule, it's not even. Sometimes just by looking at them it's hard to work out if they're even or not, but yeah, we'll build up an understanding. So another word for a polar molecule, where one end slightly negative, one end slightly positive, is the fact that it has two poles, di meaning two. So it has a dipole, two poles. So the classic example's water, a water molecule. So you've got two polar bonds. The bond between the oxygen and the hydrogen is a polar bond. The electrons spend more of their time up near the oxygen, which makes this end slightly negative. So it's working the same for each bond. So this end of the molecule is slightly negative and this end of the molecule is slightly positive. So different ways of drawing the polar molecule. For a molecule to be polar, the charges must be asymmetrical. So even though some molecules have polar bonds, so chlorine is more electronegative than the carbon, so the electrons will spend more of their time near the chlorine. So But the trouble is that there's chlorine all the way around this molecule, so it's symmetrical. It's not that the electrons are spending more time at one than the other. So this is not a polar molecule. It does have polar bonds, but it's not a polar molecule because it's not asymmetrical, not unbalanced. Alright, this is ammonia. So we've got polar bonds here. Each of these is a polar bond. And the electrons are spending more of their time up this end of the molecule, so that's slightly negative. This end down here is slightly positive. So ammonia is a polar molecule because the nitrogen is more electronegative. And the charges, the polar bonds, aren't symmetrical. Does it have a dipole? Yes, dipole, two poles. This is the same thing as saying it's a polar molecule. Is this a polar molecule? Alright, so you'd need to look up, if you've forgotten, the carbon and the hydrogen, 2.5, 2.1, the difference between them is 0.4, it's less than 0.5, so they share equally, fairly equally. Oxygen and hydrogen, the oxygen is more electronegative than the hydrogen, so the electrons spend more of their time with the oxygen. So this kind of end of the molecule, we could say, is kind of slightly negative, and this is slightly positive. So this is a polar molecule. It's not symmetrical, it's not balanced, so the polar bond here makes the whole molecule polar. This molecule, you might remember from naming, it's got two carbons, so meth, eth, it's ethanol, ethanol. So ethanol is alcohol, it's a polar molecule. Alright, there's two types of polar molecules, dipole, dipole, remember? And that's what we've been looking at. So far, we've just built up an understanding of one molecule. We haven't actually looked at the bonds between molecules yet. We've just built up what a dipole molecule is. So now we're going to look up understand what a dipole bond is, a bond between molecules. So when molecules with dipoles come near each other, the dipoles attract each other and form a very weak bond called a dipole-dipole bond. So as we know, negative charge is attracted to a positive charge. So this is one molecule and it's attracted to another molecule. It's a very weak attraction, so rather than drawing a solid line that's to show that this covalent bond, this hydrogen is very strongly bound to the chlorine with a covalent bond, rather than showing a solid line, we do a dotted line for our dipole bond. So this is another hydrogen chloride molecule, hydrogen chloride molecule. So these are all being held together by really, really weak dipole-dipole bonds. Okay, so dipole-dipole is the overarching name. When a hydrogen is bonded to either a nitrogen, oxygen or fluorine, if you look on the periodic table, you can see that nitrogen, oxygen and fluorine are all one after another, NOF. So it's a good way of remembering them. So when a hydrogen is bonded to any of these are very electronegative, then the dipole is at its strongest. So the electrons spend more of their time up near the oxygen, nitrogen or fluorine. So this particular dipole bond that forms is the strongest one of these. These are all weak ones, but this is the strongest of the weak. And so we call that a hydrogen bond, this dipole-dipole. So the classic molecules that have a bond between an oxygen and a hydrogen, nitrogen and hydrogen, and a fluorine and hydrogen are these ones, water, ammonia, and hydrogen fluoride. So even though hydrogen chloride, hydrochloric acid, is a polar molecule. It doesn't form hydrogen bonds because it's not bound to an oxygen, nitrogen or fluorine. Alright, so if we look at our intermolecular bonds between these polar molecules, how many polar molecules do we have in that picture just here? I think if I put circles around them, it makes the molecules stand out a bit more, and then you can see this is an between molecules, intermolecular bond, holding this molecule next to the, near the other molecule, holding them together, holding the water molecules together. So dipole-dipole bond, or we can call it a hydrogen bond. So there's another one down here. Okay, you need to be able to draw molecules with their intramolecular bond labelled, the covalent bond, and their intermolecular bond labelled, the hydrogen bond, or dipole-dipole bond. Alright, the more regular the hydrogen bond between the water molecules, so the more even, so these ones, if you turn them and make them regular, then your water, solid water molecules, if they're held together as a solid, becomes really clear. If they're irregular, if it's sort of all over the place, there's a bond there and then there's not another one and it's kind of all a bit messy, then your water, your ice is a bit cloudy. Okay, this is another example of intermolecular bonding between dipole molecules. So this is an ammonia, NH3. So we've got slightly negative on one end, slightly positive on the other. Another ammonia molecule, another ammonia molecule. So between them, the dotted lines between them are intermolecular bonds. So they're polar molecules. They have a dipole, each of them, two poles, two ends I should say. So they form dipole-dipole bonds between the molecules, intermolecular bonds, or we can call it hydrogen bonds because it's nitrogen attached to a hydrogen. So it also forms hydrogen bonds, the specific type of dipole-dipole bond. And this is the last one, hydrogen fluoride. How many molecules are there? Can you circle the molecules in your mind? So there's one there, there's one there, there's one there, and there's one there. So they've got covalent intramolecular bonds between them, holding the hydrogen to the fluorine. But between each molecule, you have intermolecular bonds, dipole-dipole bonds, or hydrogen bonds. So these molecules, water, ammonia and hydrogen fluoride, as well as having an electronegative atom like the nitrogen, oxygen and fluorine, very electronegative, they also have lone pairs. So the nitrogen is even more slightly negative than the oxygen and the fluorine, even more slightly negative, because it's got these negative lone pairs as well as bringing these electrons more up to this end. Alright, so that's this first type. Okay, so now we'll have a look at the other type of intermolecular force, dispersion forces. So there's other names for dispersion forces. Instantaneous dipole-induced dipole forces. So instantaneous mean happening right at that instant, or van der Waals forces. So these are all types of bonds that you get. We're mainly looking at between molecules, but you can, just between noble gas atoms, you can get these forces holding the atoms near each other. So you can see why we call them dispersion forces, because it's a much easier name than the other names. Okay, so the electrons around an atom can momentarily move to one side of the atom. So we tend to think of electrons as fixed in position next to an atom, but they can move from one side and to the other, and they might momentarily, just for that instant, move to one side of the atom and make it slightly negative, and the other side slightly positive. And then they'll move back again, and that slight negative, slight positive will stop. So if the same thing is happening in another atom next to it, and you end up with a negative on one, slightly negative, they should have that little slightly symbol on one side of the atom, and slightly positive on the other side of the other atom, then just for that instant the two atoms are attracted to each other, and we call that weak bond between the two atoms dispersion forces. So this is what happens between noble gas atoms. Okay, so the boiling point is the point that you need, the temperature that you need to turn from a liquid to a gas. You would expect these are all noble gases, they all have full outer shells. They're all found as individual atoms in the air. You would not expect them to be wanting to be attracted to another noble gas, another atom of the same type, in order to form a liquid. So when you cool them right down to minus, for radon, minus about negative 60 degrees, then the atoms have slowed down so much that the dispersion forces between the atoms, the really weak slight negative and slight positive that sometimes form, is enough to hold the atoms together at minus 60. So radon has the most electrons. It's a noble gas with the most electrons, and then as we go up the periodic table you get less and less electrons, so you get less and less chance for these slight dispersion forces to form. So less and less chance, less and less reason for one atom to be bonded to another atom as in a liquid form. Alright, so if we look at molecules, if we just look at non-polar molecules, so molecules where the electrons are definitely being shared equally, so two atoms of the same type will share electrons exactly equally. So there should be no slight positive or slight negative on either side, so that if you had another fluorine atom they would stay attracted to this fluorine molecule, I should say. However, when you look at fluorine is the smallest one, then chlorine, bromine and iodine, as you get larger and larger atoms, you get more and more electrons, so more and more chance for one side of the molecule to be slightly negative compared to the other side. So iodine molecules would be more attracted to other iodine molecules than fluorine molecules would be attracted to other fluorine. So you need, it has a higher boiling point. Iodine is actually a solid at room temperature, bromine's a liquid, and fluorine and chlorine are gases. So the dispersion forces between iodine molecules is strong enough to keep the iodine molecules together as a solid. Alright, if we look at molecules that are compounds, not just the same element, then we need to look at the bonds to see if they're non-polar. So carbon and hydrogen share fairly much equally their non-polar bonds. So you would not expect they're non-polar molecules. You would not expect methane molecules to be wanting to be attracted to each other. So the only reason that one methane molecule is attracted to the other is if the electrons that are actually flowing around between these bonds between the atom, around the atom, sometimes instead of being equally, they might flow so that they're on one side of the atom more than the other, which would make this side over here slightly negative, that side over there slightly positive. The same thing's happening with this methane. This was slightly negative, that was slightly positive. Then the negative here, slight negative here, slight positive there would make a dispersion, an intermolecular bond that's called a dispersion force between them. So that just happens momentarily, and then the electrons will flow back again and that would break. So this dispersion force, this momentary attraction, is enough to keep methane together as if you cool it down to minus 161, then the molecules are attracted to enough to turn into a liquid at that temperature. The more electrons you have, so the more atoms you have, the more electrons you have, the more chance that somewhere on the molecule the electrons will be flowing, so that one side of this bond here is slightly negative, the other side slightly positive. So for just this instant between maybe these carbons, hydrogen here, and if the same thing's happening with this molecule, this hydrogen here, so just for that instant this hydrogen is positive, this hydrogen is negative, and they're attracted to each other and they're held together. Then they'll flow back and that will stop. But after that stopped, it might be happening in a different part of the molecule or a different part of the molecule. So the more electrons you have, the more chance you have of this dispersion force forming somewhere between molecules, so the stronger the molecules are held together. So if we compared two methane molecules to two pentane molecules, which one of these, a whole lot of methane or a whole lot of pentane, which one would you expect to have the higher boiling point, the higher temperature that it turns from a liquid to a gas? So the pentane, because the pentane has more electrons flowing around, more chance for slight negative, slight positive to form, so more dispersion forces, so stronger bonds holding the pentane molecules near each other, so you need more heat to turn it into a gas where the bonds break. Okay, this is another example of a molecule which has a melting point of minus 28. Okay, one of these molecules is a polar molecule and the other one is a non-polar molecule. When you work out which is polar and which is non-polar, which one do you think would have the higher boiling point, the temperature that you need to heat it to turn it into a gas? Okay, so this one is the polar molecule because it has polar bonds. So oxygen slightly negative, hydrogen slightly positive. So they're not sharing equally. The electrons would spend more of their time near the oxygen. So you've got another polar bond here, polar bond here, polar bond here, polar bond here. So these bonds are not symmetrical. They're all sticking out of the molecule at different angles. There's no symmetry to it. So if you added them all up and worked out where the negativity was, you'd find that sort of one end of the molecule would be slightly negative and one end would be slightly positive. So it has the definition of being a polar molecule. So this one, carbons and hydrogens are sharing equally. There's only carbons and hydrogen, so it's a non-polar molecule. Alright, so both of them actually have dispersion forces. So if you were to join one glucose molecule to another, one of the reasons would be because the electrons could be flowing around to make one side even more slightly negative than the other. So they both have dispersion forces holding molecules together, but this one also has dipole-dipole bonds, slightly negative of one glucose molecule, the slight positive of the hydrogen of another glucose molecule, forming a dipole-dipole bond between them. And because oxygen is attached to hydrogen, it's also, that dipole would be a hydrogen bond, which is even stronger. These molecules, cyclohexane, would only have dispersion forces between one cyclohexane molecule and another cyclohexane molecule. So glucose is kind of a solid, almost like a really thick liquid at room temperature, and cyclohexane is very runny, really runny, like water liquid.